So before we start, I probably should explain the setup a little bit. On the left hand side we have Rust, on the right hand side we have a color output which is currently being rendered by Vulkan. And it's actually interactive, so if I change some value on the left hand side, it updates accordingly. And so, and what happens is, this uses something called rlsl, which is a compiler that can translate Rust to SPRV, which is a shading language for Vulkan. And you don't really need to know what that means. You only need to know what the fragment shader does. And essentially the fragment shader gets some input and produces some output. And in this case it takes in the UV coordinates and the time, and it produces a vector 4. And in this case it just produces a single color for every pixel. And sort of the fragment shader kind of, you currently can specify the parameters by inputs, saying that UV is an input, so it kind of changes for every pixel, and it is a vector 2. And the time is uniform, which means it's kind of constant for the whole execution of the fragment shader. So essentially all the fragment, the entry point here for the fragment shader does is it just calls something render function, which is defined at the top here, which also takes the UV in and the time and produces a vector 4. Okay, and so to actually display we can actually display the UV coordinates relatively simple. So we can just do UV, but of course it doesn't really compile, and it shouldn't actually compile. Okay, that's 0 because it's actually vector 2, but we expect a vector 4, so we can easily fix this by calling something like saying 2. And essentially it turns a vector 2 into a vector 4. So we say the Z component should be 0 and the W component should be 1. So and if we save this, we get the according output, and you can see that so we get kind of like 0, 0 value at the top, and the bottom is green, and the top right is completely red. And so this kind of translates to something. I sketch this a little bit out here. So we kind of have this image here, and we have the UV coordinate is on the left here. It goes down from 0 to 1, and the X component goes to the right, and also from 0 to 1. Okay, and so we kind of want to start with this. We kind of want to imagine we kind of want to do a little bit of raycasting. And so how this really works is, we have some kind of origin or some kind of starting point, and we want to shoot some kind of ray, and I explain a little bit of what this really is. So we kind of shoot some kind of line, and at one point it hits the sphere. Okay, and so essentially, and we can get we can ask what color is this, what color should this be, and we can then write it into the image and display it. And so how we really do this is, first we kind of need to get the origin from the top left to the center, which is relatively easy to do. So we can just start off by defining a coordinate, and we can just say okay, how do we do this? We can say we can scale it by 2, and we subtract -1. So instead it was from 0 to 1. Now the components will be 0 to 2, and we subtract 1, so it will be from -1 to 1. Okay, and this is actually a vector 2, but we kind of want to be in 3D space, so we can do extend and yeah, and just say extend to 0, 0. Now we have essentially moved this from top left to the center, so we kind of have like some kind of coordinate system that would look like this. And essentially we get for every pixel, so this kind of fragment shader gets executed for every pixel, and so we get a vector actually that points to this pixel location, right? So we get like maybe this and another one, or to this pixel location. So to actually shoot a ray, we kind of need two things here. We can we can first define the array. We say the array kind of needs some kind of origin, which will be a vector free of floating points. And what to do here? And we also want to have a direction where we shoot array, which is also be a vector free. But I go a little bit further and say this should be unit vector, which we can do, which we cannot do. Okay, which we can do, right? So this is kind of like a simple abstraction that always forces the vector to be normalized or to be of length 1. And so to translate this in this, to get the direction is fairly simple. We need some kind of vector that points to our image, which we can define. We can just call it the look vector, and we say it will be also vector free. And we can say maybe it looks like this, so 0, 0, 1, which translates to it will be of length 1 into the z direction. And then we can just add the pixel coordinate to get to this kind of vector here, right? And so we can just do this. And we call this, we can call this the direction of the coordinate, or we could call it look plus the coordinate. And it should compile. And why is it so slow? And okay. And we kind of want the origin. We can origin, and we just say vector tree, and we have something like a single, which basically, and it's also player 2, which basically says every component should be initialized to 0 to this value here. So now we can actually create this array by saying origin and the direction. So but the direction is always normalized, so this kind of doesn't really work. So we call it in compile time. So, and which means I have some function which is not a good name, but it's called toUnit, which automatically turns the vector into unit vector. So this works out nicely. So kind of what raycasting here in this case does is we have this kind of vector now. We start from this position, and now we need to figure out, and we have some kind of sphere in our scene, and now we kind of need to figure out how much should we scale this vector from this position until we hit the sphere. Okay. And so the first thing we can do is okay, maybe we should derive a copy clone for this, and we can implement some functions on it. So let's see, let's call this position, and we can actually pointers do work. They don't really work in SPV, but I kind of optimized some ways. So you can just do self, or you could do by copy, right? So we can do self. So also works. And so we want a function which we call position, which takes in the t, and it should output vector free. And so we can just do self position times self direction times t. So the I have like the reference here. Does it compile? Oh, it's not. Sorry, it's origin, and this should be a plus, of course. So we cannot directly multiply right now with a unit vector, so I kind of need to deref it because it implements deref and all this kind of thing works. So all generics, and it just works. And now we have the position. Okay, what else do we need? The next thing we kind of need is the sphere itself. So let's define this. We define sphere, and the sphere should have also origin. It will also be of vector free, and it should have a radius of floating point. And let's actually do no. And let's actually also make it copy clone. So let's create the sphere. we can do let's do position. We can do vector free. Gives it some position. And we give it a radius of, let's say, 3. Let's reformat this. And this should compile, right? Yeah, it compiles. And I kind of wonder why it is so slow. Okay, but now that it compiled, we now have to sort of figure out how we do the intersection. Okay, so we now have our array, which we always shoot this from the origin, and always to the always through the pixel location. And now we kind of need to figure out how far we need to scale it, you know, until we reach the sphere. And of course, we could have like some kind of array that could look like this, you know, it could look like this. And of course, there is no value that we can input here, or no real value that we can input here that actually would be on a sphere. So this doesn't work. And you can actually do this with math, but I kind of don't want to do this right now because it takes a little bit of time. So I just copy paste it for now. But before we do this, before we actually copy paste, let's actually do something. Actually create something like the array hit. And so when we want to raycast, we kind of want to know at this point, okay, which position in 3D space is this point, and we kind of want to get the normal. And the normal, if this is a sphere and this is the surface of the sphere, then the normal would point away from it. Okay, and so we can create a little bit of array hit struct. Say it should get it should have a position of vector 3, and it should have a normal which should be of vector 3, and maybe we should also make this a unit vector, because normals usually are unit vectors. And so let's define on a sphere a new function called intersect, and which takes in the array, and it outputs array hit, an optional, and we can do none for now. Let's reformat this. This compiles. So this next thing that's kind of interesting is actually a lot of features in Rust kind of just work. So you can return options from here, which option kind of says, okay, you know, we didn't hit anything, and should return none. Okay, now I can copy some of the math code in here, and this is kind of derived by taking the implicit equation of the surface of the sphere, inserting the array equation of the position, and then solving for t, and you get essentially just a quadratic equation, which you can solve with the ABC formula. And I have implemented this actually in my math library, which I call the quadratic. And so all we need to do is call this function with a, b, and c. And we can actually have a look at this function. So this function, you know, it takes in the 3 floats, and it produces an option of vector 2. So the ABC formula kind of gives you 2 results, but only if the discriminant is positive. Otherwise, we get a non back. And I could have used a tuple here, but the vector is a little bit more is better because it has more functionality on it. For example, we can do the question mark operator from Rust, and then we can do min. Okay, so and why do we choose min? And we can just see this relatively easy if we shoot some array. And where's the key binding here? And so there are actually 2 intersection points that we have, but we want to get the closest one, right? So we just do them in, but of course something else could happen. We could have happened some kind of sphere behind us, and this also works, right? So we also get the hit location here, but it will be negative. The t has to be negative here, and so let's check for this. So if t is actually negative, oh god. If t is actually negative, then we kind of return none directly. So we say we didn't hit anything. And yeah, that's basically it. So now we have the t value, right? So we know how far we need to scale it, and we already implemented this in the ray. So we can just do ray position with the t value, which gives us the position. And so now we need to compute the normal, and the normal is for a sphere is absolutely trivial to compute. For example, we have the origin here, and we want, if we hit this point here, we want to get the normal here, and essentially we just can connect them together, right, and normalize this vector. So this will be from the position that we just calculated. We subtract the origin from the sphere, and now we can create the array hit. So let's array hit, and we input the position where I can complete and the hit, but of course it doesn't compile because hit is not a unit vector, right? So we just need to do what I'm doing in the normal, and the normal 2 unit. So, and that's basically it. And now we can do, and we can return it. Okay, and so yeah, now we have the sphere, and now we can actually do the ray tracing or the raycasting. So we can just do color, and we can let some hit from where is it? Sphere. No, that's not the correct sphere. From sphere intersect, and we do the ray. So I will get this inside. So maybe let's see. I will put the what happened here. So put this in the else branch now, and let's do something like vector free single 1.0, and let's remove this and return the color. And it doesn't compile. Oh right, I've made a vector 4. Let's reformat this. And it's of course not extend 1, but it just extend. And now we need to do extend here. Okay, boom. And we kind of have a sphere, a white sphere here. So essentially what happens is, okay, we say, did the array hit the sphere? If yes, we are in the true branch, and we just say, okay, output the color white, or else we will output the UV. But UV is kind of a little bit ugly to look at, so let's replace it with something a little bit nicer. So we can essentially do a skybox very easily by linear interpolation. So let's do white. Let's do vector free single and 1.0. And so how linear interpolation kind of works is, okay, we have a variable y, and we know it starts from the top and goes to the bottom, and it is between 0 and 1, and so we can just say, okay, if y is 0, and then we can say, okay, this should be blue, and this should be completely white, and so, and if in the middle, then it will be 50% white, 50% blue, and so we can easily compute an easy gradient with linear interpolation, and this is very easy. We can just do blue, lerp, white, and we use the UV, the y coordinate for the UVs. And you can see we have, like, on the top is blue, on the bottom is white, and we get sort of a nice gradient going, which it's a bit nicer to look at. So of course, just having a white sphere is not super fun, so maybe you can actually animate a little bit. So we can create a vector 2 from polar coordinates, and if you don't really know what polar coordinates are, it's essentially coordinates where instead of specifying the location explicitly, you can calculate it by, or just specify the angle and the distance or the radius. So we can say, for example, something, we now have time, which will be the angle in radians, and so it is kind of, and time actually I didn't say that, I think, is in seconds, and so we get 1 radians per second, and we can say you know, something like 3.0, but of course it doesn't really work right now. It doesn't compile because of course it's a vector 2, and so we can extend it, and we want to extend it by some bigger value, like 10. And you can see, of course it rotates in the wrong direction because our coordinate system is actually a little bit upside down, right? Because the y coordinate faces downwards, like this, and so it rotates in the wrong direction by default, or maybe the right one. But we can easily fix this by multiplying the y coordinates with -1. So I'm not sure what the best possible solution would here be. Maybe we can just do vector 3. We do 1.0, and so something like this, where we, right? Okay, so we only flip the y coordinate. And we could probably have done it a little bit better, but it works. 3 from a bit, and so now we kind of want to get a little bit of shading in there, so we can define some kind of light. Let's define it out here. Let's say light is at position, I don't know, let's say it's at position 0, 0.5, or 10, 5 or something, doesn't really matter. And so what we can now do is let's also define better sphere color. So we can give it some kind of value, maybe, I'm not sure. And I don't know, something like this maybe. And so let's return the sphere color, and it should change to another color. And okay. So now what we can do is we can do some kind of simple Phong shading, where we essentially do essentially we have some kind of sphere here, and we have defined our light source, which maybe would be up here, and we have our normal for some point. And what we can just do is we can just get a vector to our light vector, or what did I do? Okay, right, something like this, and we can normalize it maybe to something like this, and we can get the cosine angle between them. And so we just do light vector, and so we want to, from the light to the hit, where we to a hit position, but we also need to and so we can just compute, we have to normalize it, the light vector, so it will be unit vector. Okay, and so we can just compute the cosine value for this easily with the dot product. So we can just do the light vector now, dotted with the normal of the sphere, normal of the hit. So the hit normal, and this is actually, I think, we also need to ref it, and now we can then multiply it just by the sphere, and you can see that it gives you a nice shading, right? So, and that was basically it. We could go a little bit further, and we could play maybe a bit with the radius. We could also animate the radius. For example, we could do get the cosine of the time, but the cosine will be between -1 and 1, and we kind of don't want a negative radius, so we can just do take the absolute value, and you can see it will animate nicely, but we can make this maybe a bit bigger. Okay, and yeah, that's basically it. Maybe we can talk about libraries a bit. So libraries work just like they do in Rust. You can specify it in cargo, and it will just work. And for example, we can see something here called rlsl math, which is the math library that I wrote specifically for this compiler. It was just easier for me to write my own library, but you can technically use any other library that you want. There are a few things that you might need to do. For example, you might want to annotate some of the vectors with the attributes here, like this is a vector 4. It's a little bit intrusive right now. I'm thinking about some traits that you can implement for the libraries, which would probably be better. But you don't even have to do this. This basically just maps this kind of struct to this BV intrinsic. But it's kind of important because for the entry point, if I open the entry point again, and this was where was it? If I open the entry point again, everything in here has to be intrinsic, so it has to map to a specific SPV vector in SPV code. And we can actually also look at the generated code, and this would be, so this is the file that we generate, that we compile to. You know, it's kind of big right now. A lot of debug information in here that you can strip away if you want to. Yeah, we can always have a look at this, but it's not really maybe the most readable format. But this is essentially what you can load in Vulkan. Okay. Yeah. So that was basically it. I hope you enjoyed it.